Welcome to 4.7. Actually, this is a brand new unit overall. This is your first set of notes. So this is some more integration that technically could have gone on our last set of notes, but we wanted to go ahead and just put them onto this set of, or this unit instead. So that way it didn't get so bombarded on the last unit. So today we're going to talk trig substitution with inverse trig integration and other techniques of integration. Okay. Yeah, this is kind of a mouthful, but I promise you it'll be okay. So before we get into trig substitution, I want you to remember these three Pythagorean identities, because that's what we're mostly going to work with today. So our Pythagorean identities are sine squared plus cosine squared equals 1. And then the other two are just modifications of these, okay? So you've got 1 plus tangent squared equals secant squared. And then at the same time, you've got 1 plus cotangent squared equals cosecant squared theta. Okay, we are going to focus mostly on these two today. Technically, you could also use this last one, but we're going to just mainly stick with the first two. Okay, so let's jump right in. So let's say I have the integral of dx over 1, the square root of 1 minus x squared. Now, for this one, my first initial thought is, okay, it's a fraction. Let me see if I can do a natural log situation here. Well, it's not just natural log of u over u, because I have that radical in the denominator. So natural log won't work. A basic u sub won't work either, because even if I did u was equal to 1 minus x squared, I don't have the derivative of it nearby, nor would I be able to make a simple modification in terms of u like we've done in the past. So in this case, I have to try something totally different. And that thing that's totally different is trig substitution, okay? Now, this isn't something that I would have anticipated that you could have easily looked at and been like, oh my gosh, I'll just do some trig substitution. No, this is a new tool. This is a new feature. So if you think to yourself at some point like, well, I never would have thought of that, that's okay. I'm teaching you something new. Okay, so you might not recognize this one, but I want to use the Pythagorean identity sine squared theta. Why is this sine squared? Okay, well that didn't write like I wanted it. Let me try this one more time. I want to write out sine squared theta plus cosine squared theta equals 1. Okay. Again, you're probably thinking like, where's she going with this? Just bear with me here for a second. Okay. So I have a 1 minus x squared in my denominator. Well, I know that if I were to rearrange this, like if I were to move this over, I would have cosine squared theta equals 1 minus sine squared theta. I could have also subtracted the cosine squared to the other side. I just went ahead and did the sine squared for right now. So while this is close to this, it's not quite the same, but basically what I want to do is, instead of having an x squared right here, I want to replace it with sine squared. Okay, so up to this point we've done u substitution. This is a trig substitution, where instead of replacing an expression of x in terms of u, we are replacing x, or sometimes a small expression of x, like a small modification of x, in terms of sine, cosine, or tangent theta. Okay, so what I want us to do is to let sine theta equal x. Okay, but up here I actually have x squared, so that means sine squared theta is the same thing as x squared. Okay, so if I wanted to rewrite this integral, so far what I could rewrite, I can't replace dx, I haven't done anything with that yet, but in my denominator I would have the square root of 1 minus sine squared theta. Okay, I'm not done with that integral yet, obviously, because I need to replace dx, but this is where I'm at so far. Okay, so speaking of dx, I've got to have something to go there. So let's go back down here. Sine of theta is x. To get dx, I have to take the derivative of both sides of this with respect to x. Now, this is in terms of theta, so just like we've done in the past, when I take the derivative of of a variable that's not x, but I want to take the derivative in terms of x, I have to use implicit differentiation. So this is going to turn into the cosine of theta d theta dx is equal to 1. Okay, we kind of did this with a u substitution. Remember, we did du dx is equal to, and then you took the derivative of whatever your u was equal to. So this is the same idea. It's just that we have a cosine situation, or a sine here, so I have to take the derivative of the outside, which is cosine, but then the derivative of theta itself, since I don't know what theta is in terms of x, I have to use implicit and have d theta dx right here. Okay, but then just like I've done with a u substitution, this dx right here is not in a place that's convenient for me. If I were to move it to the other side by multiplying by dx, then it's going to be much more convenient. And I can say that the cosine of theta d theta is equal to dx. Okay, well, that's convenient because I needed a replacement for dx right here. Well, now I have it. So now I can go ahead and write cosine of theta d theta. Now, you're probably looking at this going, hey, wait a minute, that looks actually far more confusing than what we started with, because now you've got two trig functions in there and some other nonsense. I understand, okay, but here's what we can do. If you look at 1 minus sine squared, remember, that's the same thing as cosine squared. So I can rewrite the denominator down here in terms of cosine squared because I have that Pythagorean identity. So I've got cosine of theta over the square root of cosine theta. Oops, I forgot the squared. Cosine squared theta d theta. Okay, so remember 1 minus sine squared is the same thing as cosine squared. So I just rewrote it as cosine squared. But I have cosine squared inside a radical, so this becomes cosine theta d theta over cosine theta. Oh, well, this is even better because then those two things reduce and I just have the integral of d theta. Well, the integral of d theta is just theta plus c. But like before when I did a u sub, I had a very specific or explicit expression for u in terms of x, but now I don't have anything in terms of theta. So I'm going to go to this thing right here where I started. If the sine of theta is equal to x, how do you undo sine? What's the opposite function of sine? It's not cosine, guys. Don't say that, okay? If the sine of theta is equal to x, that means theta is equal to arc sine or sine inverse of x. Okay, so that means down here where I have theta plus c, this is the same thing as the arc sine of x plus c. So this whole nasty integral is actually arc sine of x plus c, but we proved it using trig substitution. In the future, we won't necessarily have to prove that because hopefully we will recognize this right off the bat. But yeah, that's how you do a trig substitution. I feel like one example might not be enough today, so let's go ahead and look at another one. This one is the antiderivative of dx over the square root of 4 minus x squared. So it looks somewhat similar to the last problem. Oh crap, but I have this 4 right here. I only know how to do trig substitution if I have a 1 minus x squared or a 1 minus something squared. Basically, I need a 1 right here because of this Pythagorean identity. But now I have this 4. So what do I do with the 4? Well, I am going to factor out that 4. I'm going to make this integral dx of the square root of 4 times 1 minus x squared over 4. Because if I take a 4 out for the first term, I'm left with the 1. Take a 4 out of x squared, it's just x squared over 4 because I don't know what x squared is. Okay? So that's what I've got so far. From here, let's see, what shall we do? Well, I replaced x squared last time with sine squared, but now I've got x squared over 4. So I'm going to say let sine squared of theta equal x squared over 4. I'm going to do this whole term this time. It's going to be sine squared theta. All right. Again, you might be wondering, what is this crazy fool doing? Just bear with me here on this for a second. So then I could rewrite my integral. So far, I have the square root of 4 times 1 minus sine squared theta. And we already know from past experience what's probably going to happen here, but we're gonna keep going here. So speaking of, I guess I need to figure out how to get dx. So to do that, well, if sine of theta is x, if sine squared theta is x squared over 4, that means sine of theta is x over 2 by taking the square root of both sides. And so I can take the derivative of that and get cosine theta d theta is equal to 1/2 dx. Okay, again, remember this is d theta over dx, but the dx automatically moves to the other side, just like we did during u substitution. Okay, so now I've got 1/2 dx. Oh, but I didn't want a 1/2 dx. I just want dx. So go ahead and just multiply and make that 2 cosine theta d theta equals dx. So far, so good. So now I can put this guy in my numerator in place of dx. So I've got 2 cosine theta d theta all over the square root of 4 times the quantity 1 minus sine squared theta. So now I'm in a good spot where everything in my original integral has been rewritten in terms of theta instead of x. So I can start to clean this up using our Pythagorean identities, and then hopefully this works out really well. So we've got 2 cosine theta d theta over the square root of 4 times 1 minus sine squared is the same thing as cosine squared theta. And then it's under a radical here, so 2 cosine theta d theta all over the square root of 4 cosine squared is the same thing as 2 cosine theta. Those reduce are the integral of d theta, which we know is just theta plus c. Okay. However, I don't have my expression for theta yet. I'm supposed to get that from this guy right here. Well, if the sine of theta is x over 2, that means theta is equal to the arc sine of x over 2. So I can bring that back here and say that arc sine of x over 2 plus c is the same thing as theta plus c. So my original integral that started out, it's very similar to the last one, but now it has this 4 right here. This is arc sine of x over 2 plus c. So that makes me wonder, what if this 4 had been a 9? How would that change this whole process? Well, if I had a 9 here, a 9 here would turn into a 3 here. So then that would become arc sine of x over 3 plus c. Does everybody follow on that one? Basically, if this had been, or if this had been a 2, if the 4 had been a 2, whatever the square root of that number is, it's going to go in the denominator right there. Okay? Because no matter what it is, you would have to factor it out just like you did the 4 and follow through with the same process to find out what the antiderivative is. Okay? So that's how you find arc sine, or actually the antiderivative of a function that ends up being arc sine. Okay? Let's try something new here. So this one's different. It's got dx over 2 plus 9x squared. So not a radical anymore in the denominator. So I'm not going to be able to use the same trig identity that I did in the past. This time I'm going to focus on the other one that I mentioned at the beginning of the notes here. I'm going to look at 1 plus tangent squared theta is equal to secant squared theta. Okay? Now you'll notice here I don't have a 2, or I have a 2 instead of a 1. So basically, if I have something that's close to what I need, I can modify it to make it what I actually want. So last time I factored out a 4, how about we factor out a 2? So dx is going to be 2, or dx over 2 times 1 plus 9 over 2 x squared. Okay? In order to do something with this, I have to have a 1. So instead of a 2, I just divide, I factor out a 2 like this, and I just make it a 1, and then the 9x squared over 2 just becomes 9 halves x squared, okay? So far I haven't changed the mathematical value of my integral. I've just modified it in a way that makes it a little bit more friendly to what I need here in a second. So last time we were using sign because we had 1 minus x squared or 1 minus x squared over 4. Now I have a positive, so 1 plus. So instead of using sign, I'm going to use tangent. So I'm going to say let tangent squared theta equal 9 over 2 x squared. Okay, which if I were to do that, that means that the tangent of theta is equal to, take the square root of everything, so 3 over root 2 x. Okay, so let me go ahead and start rewriting some of this over here. So you've got, let's see, the integral. I don't have a expression for dx yet, so I'm just going to leave that blank for right now. 2 times 1 plus tangent squared theta. All right, so I'm off to a good start, but I need to find dx right here. Well, I do that by taking the derivative of this. The derivative of tangent theta is secant squared theta d theta, and then 3 over root 2 the dx. Because remember, again, it would be d theta over dx, and you move the dx to the other side. Okay? But I don't want this thing. I just want dx. So I'm going to multiply it by the reciprocal and say that root 2 over 3 secant squared theta d theta is equal to dx. So now I can replace my numerator with all of this. So I've got root 2 over 3 secant squared theta d theta. Okay, again, it actually looks a bit more complicated at first than what we were going for, but I promise it'll clean itself up. So I'm going to have actually like root 2 over 3 over 2. This whole thing is one big constant. I'm going to move that out front and make that root 2 over 6. Okay, because root 2 over 3, and then times 1/2, just root 2 over 6. So secant squared theta d theta over 1 plus tangent squared, well, that is secant squared theta. So that goes away, and this becomes root 2 over 6 times the integral of d theta, which we know that that's just root 2 over 6 theta plus c. Theta, I didn't come up with an expression for that yet, but right here, if tangent of theta is this guy, using the same process that we did earlier, that means theta is equal to the arc tan of root 3 over, no, I keep writing root 3. I think maybe I'm stuck in my unit circle ways here. That's okay, we got this. So theta is equal to arc tan 3 over root 2x. So I'm going to bring this over here and say that root 2 over 6 times theta. So I've got root 2 over 6 arc tan 3 over root 2x plus c. Whew, that is a lot. So root 2 over 6 arc tan 3 over root 2x plus c. Yeah. So you're probably thinking like, Murphin, there's got to be, good Lord, there's got to be a better way to do this. Well, so this is mathematically how you would work this one. But if you wanted kind of the shortcut, well, hey, we've got one of those for you. Okay. So do you remember these from back in your derivative days? Like it's been a little while, but back in the day of when we did derivatives, remember we had the derivative of arc sine was u prime over 1 minus u squared. Derivative of arc cosine is just the negative of that. Arc tan was u prime over 1 plus u squared. Arc cotangent is just the negative of that. Arc secant, I put a little star beside arc secant, arc cosecant, just because we don't use those quite as often. It's still good to have those memorized, but they just don't come up very, very much. Not sure why, but we tend to stick with the other four more often, okay? So remember, just like we've done in the past, if we've learned how to go one direction, like go from derivatives this way, now to go the other direction, we take the antiderivative. So now, if I had du over the square root of a squared minus u squared, that's equal to arc sine of u over a plus c. What? That doesn't look like what we had before. Hold on. It actually does. Okay. So go ahead and write this one down. Okay. And then I'm going to go back to that second example that we did just now. Okay. So hopefully you got this written down. If not, pause it, write it down, and then come back. So let's go back to this guy right here. Now, we just wrote down that the integral of du over the square root of a squared minus u squared is equal to, let's see, oh, I already forgot, is arc sine u over a plus c. Okay, I didn't forget, I just had a moment. We'll go with that. Okay, so then if that's the case here, let's write this in a different color. So that way when you're referring to this later, you can tell where we did something different. So then in this case, a equals 2, u equals x. So then dx over square root of 4 minus x squared, I just plug them into my little equation here, and that's the same thing as arc sine of x over 2 plus c, which is the exact same thing that we got earlier when we did it using trig substitution. So trig substitution proves how inverse trig works, but now from this point on, you don't have to do this formal process. You could just memorize this right here and go with that. Okay, I just wanted you to see how it worked before I just said, hey, this is what it is. Because otherwise you're like, where is all this stuff coming from? Well, now you know. Okay, so, let me go one more slide. So then we also have du over a squared plus u squared is equal to 1 over a arctan u over a plus c. Okay, well, we just did an arctan problem. So again, write this one down, memorize it. Okay. And then let's go back to this one. We know that antiderivative of du over, what was it here? A squared plus u squared is equal to 1. I'm going to run out of room here. Hang on. Boop. 1 over a arc tan u over a plus c. So in this case, we have to identify what is u and du and all that good stuff. Okay. So in this case, we're going to let a is going to be equal to, well, if this guy is a squared, that means a is the square root of 2, so root 2. U is going to be 3x in this case. The last problem it was just an x, but this time we have that 9 right here, so the square root of 9x squared is 3x. So that means du is going to be 3 dx, which I don't have a 3 up here, so I'm going to make that 1/3 du is equal to dx. So then I would rewrite it as, let's see, I'm going to have 1/3 du over a squared, because this is 2, plus 3x squared, 3x quantity squared, or u squared. Okay, so then I've got 1/3 times 1 over a arc tan u over a plus c, 1/3 times 1 over root 2 arc tan 3x over root 2 plus c. it doesn't look exactly like what we had a minute ago, only because I haven't simplified my radical yet. If I were to simplify this radical, that would be root 2 over 2 times 1/3. So this becomes root 2 over 6 arc tan root, oh my gosh, I did it again, 3 over root 2x plus c, which is identical to what we had before. Okay, so yet again, you could do this whole long process using trig substitution, or you could memorize your inverse trig rules. Either way works for me. You pick what you would like to do. Okay, there was one more that we needed to talk about. Arc secant is whenever you have du over u times square root of u squared minus a squared, it is 1 over a arc secant absolute value of u over a plus c. Now, I'm not going to do the formal trig substitution for this one because, again, we don't use arc secant as much as we do arc tan, cotangent, and all the other ones. But you are welcome to look this up. I believe Khan Academy has it, or even Prof. Rob Up, one of those. And then also down here, you'll notice I only have 3 of them up here, but we have 6 total trig functions. Well, remember, arc sine and arc cosine looked very similar. They were just opposites of each other in terms of one was positive, one was negative. So if I have a negative out front, it's just going to be arc cosine. If I have a negative out front, it's going to be arc cotangent. Okay, so not a huge deal, but just something to point out for you guys. Okay, so again, you can memorize these. I would write these on your Stuff You Must Know Cold formula chart, or you could do the formal trig substitution process. I'm good with it either way, but you know, when it comes to the sake of time, you're probably going to want to have this process memorized. Okay, so now let's put all of this stuff together of everything we've done with integration and just work a couple integral problems, okay? X plus 2 over the square root of 4 minus x squared dx. Now, we just saw something a minute ago with this, and that became an arc sine problem, right? But that was not when we had this stuff up top. We only had this in the denominator and like a dx up top. So, we're close, but not quite. Okay? Well, so in this situation, when I have x plus 2 in the numerator, I could split this integral up into 2 separate integrals. I can make this x over the square root of 4 minus x squared plus, dx, plus the integral of 2 over square root of 4 minus x squared dx. Okay? Well, then this one I could do with a pretty simple u substitution, because this would be u, a modification of this would be du. Okay, and then over here, I can just bring my 2 out front, and then, oh, lo and behold, I have my arc sine. So I've got basic u sub over here, but then I have inverse trig on this one. Okay, so let's okay, let me make this in 2 different colors here. Oh, nope, not what I wanted to do. Let's see if I can get that to ungroup. Yeah, perfect. Let's make that purple. Maybe. There we go. Okay, so let's do this one first. I've got the integral of x dx over the square root 4 minus x squared. I'm going to let u equal 4 minus x squared. Du is equal to negative 2x dx. Right? So far so good. I have x dx in the numerator, not negative 2, so negative 1/2 du is equal to x dx. Okay? So then I go to my rewrite, and I'm going to have negative 1/2 the integral of, let's see, du over, well, u to the 1/2, or root u, which is the same thing as negative 1/2 u to the negative 1/2 du. So then this is going to become negative 1/2 times, well, actually, you know what? I'm going to pause that. Pause. I don't want to take the antiderivative yet. Oh, now it's not going to let me erase. Come on. Maybe. Maybe not. It really wanted me to keep working. That's interesting. Oh, the program is freezing. That is awesome. All right, I got it to unfreeze and, erase. Okay, so this is my new integral, my rewritten version for this guy. Okay. Let's see. So then I'm going to have, well, I guess I erase that. I could keep going. You know what? -1/2 times 2 u to the 1/2 plus c. So this is, well, -1/2 times 2. So negative, and then square root of 4 minus x squared plus c. So that's just for the first part. All right. I'm going to add that to this guy right here. Well, this is the same thing as 2 times integral of dx over square root of 4 minus x squared. And again, this is an inverse, or this is an arc sign where a is equal to 2 and u is equal to x. So this is going to be 2 arc sine of x over 2 plus c. We did that because we have that from the last bit, and so then I add these two together, and the c's just combine because I don't know what they are anyway, so we just combine them to 1. So my overall integral, this whole thing turns into, I'll write this, so the antiderivative of x plus 2 over square root of 4 minus x squared dx equals negative square root 4 minus x squared plus 2 arc sine x over 2 plus c. So to do this problem, I had to recognize that I could break apart this fraction into 2 separate integrals, integrate one of them using basic u sub rules, integrate the other one using inverse trig, and then boom, done. Add those results at the end and I get my answer. Okay? That seems doable. Yeah. All right, let's try something new. Dx over x squared minus 4x plus 7. Well, this doesn't look like a basic u sub because in the denominator I have x squared minus 4x plus 7, but the derivative of that would be like a 2x minus 4 situation. I just have a 1 dx in my numerator, so it's not that. Last time I was able to break apart my fraction. I can't do that now because, well, you cannot break up the denominator. I hope you guys remember that. You can break up the numerator. That's okay. Denominator, not so much. Okay? So we're going to do something new here. Again, I wouldn't have anticipated for you to think of this. Maybe you did, maybe you didn't. But we're going to complete the square in the denominator. And see where that takes us, okay? Now, if you don't remember how to complete the square, this is one of those times where you're going to need to pause this video, go look up on Khan Academy, Prof. Rob Bob, somewhere else in, I believe, Algebra 2, and possibly even in Algebra 1, how to complete the square, okay? I'm just going to go ahead and do this under the assumption that we know how. If you don't, you need to go back and figure that out. So, completing the square. So I'm just going to look at x squared minus 4x plus 7. All right, so to complete the square, the first thing I want to do, put a little blank here, and then minus a blank here, okay? I'm going to add something and then at the same time subtract it, so that way I'm not changing the mathematical value of my expression here, okay? Some people complete the square by putting an equal sign, and then what they do to one side, they do to the other side. That's when you have an equation. I don't have an equation, I have an expression. So what I do here, I have to also undo it at the same time so I don't change the mathematical value, okay? To figure out what goes here, I take half of this term, half of my middle term, and I square it. Well, half of my middle term is 2, so squared would be 4. If I add 4 here, I need to go ahead and subtract 4 over here so that way it balances, okay? And so then to complete the square, I'm going to factor this to x minus 2 squared plus 3, okay? So now if I were to rewrite this original integral as dx over x minus 2 squared plus 3, well, now it's in a little bit friendlier format, and I can do an inverse trig situation on this one, okay? Again, I don't want to do the whole formal process like we did before. I just want to use the trick. So is this arc sine? Is it arc tan? Or is it arc secant or cosecant? Which one do you think? Well, it's a plus and there's no square root, so it's got to be arc tan. So if that's the case, remember arc tan is in the form of du over a squared plus u squared. Okay, that's arc tan. So I need to somehow figure out how to make that work over here. So I'm going to say that let u equal x minus 2. And then A is always a constant of some sort. If you haven't picked up on that so far, U is either X or an expression of X, and then A is always just a constant. So A is root 3, and then dx is just wrong side. Du, come back. Du is dx, okay? So if I know that this is going to turn into 1 over A arc tan u over a plus c, plugging in the numbers that I have from over here, 1 over root 3 arc tan u is x minus 2, so x minus 2 all over root 3 plus c. So we're kind of combining lots of things here today. We did a I'm going to put that in parentheses. I might clean that up a little bit. We just learned how to do inverse trig today, so that's where this process came in, but we couldn't do that yet on this problem until I had completed the square. So whenever you have some new integrals that you're not sure what to do, well, maybe try long division, try separating the fractions, try inverse trig, try completing the square. Like you're now at the point where I've given you a variety of tools. Just like when you're trying to, do anything else, like, do I need a screwdriver? Do I need a wrench? Do I need a hammer? What do I need? I just got to try something and figure out, okay? So these are just different math tools that you now have to do integrals, okay? So then you're going to use one of those on this next problem. Find the area of the region bounded by the graph of f of x over square root of 3x minus x squared. The x-axis, the lines x equals 3/2 and x equals 9/4. All right, so essentially I'm finding the definite integral from 3/2 to 9/4 of dx over the square root of 3x minus x squared. Okay, so going back into my toolbox of all the things that I've done with integrals, I can't do a basic u sub because there's no derivative of this in the numerator. I can't do natural log because it's not just a simple u prime over u. So then, so I've got a square root and then the things are subtracted. So it looks a lot like arc sine. But in order for me to use arc sine, it needs to look like, arc sine of u over a plus c was from the integral of du over square root of a squared minus u squared, okay? So it's close to that, but not quite. So how do I get this to look like this? Well, I'm going to use the same tool that I just did on the last slide, and I'm going to have to complete the square, okay? Complete the square for just that guy. So I've got 3x minus x squared. We don't like to write it like that. We're going to make this negative x squared plus 3x. And then I always factor out the coefficient out front. So I've got negative x squared minus 3x plus some blank right here that I have to figure out. And then minus, so if I add it, I have to subtract it. But whatever I'm adding here is getting multiplied by a negative. So whatever I have to subtract, I need to multiply it by the same negative that I have out front. So that way it actually balances, because now effectively here I'm subtracting a term, and so here I need to be adding a term as well. Okay. half the middle term squared. So half the middle term is 3 over 2. I can just write that 3 over 2 squared. But over here I'll make that 9/4. And it's sometimes kind of nice to leave it like this, because then you have negative x minus 3/2 quantity squared, and then plus 9/4 is how you have the square completed on that. Okay, so then I can replace 3x minus x squared with this right here. So then I'm going to have, let's go over here. Got all this room. 3/2 9/4 dx over the square root. To make it also look like a squared minus u squared, I'm going to go ahead and say 9/4 minus x minus 3/2 quantity squared. Okay, now it's in the format of what I'm a little bit more familiar with here. Okay, well now this is just an arc sine situation. So what I'm going to do is recognize, if I wanted to, I could just go ahead and solve this from here. Yeah, I think I will actually. So a is this guy, a squared is here, u squared is here. So this is going to turn into 1, no, that's arctan. My bad. This is going to be arc sine of u, which is x minus 3/2, x minus 3/2 over a, which is also 3/2. Normally I would say plus c. I don't want to say plus c because we've got bounds. So 3/2 and 9/4. Okay, so I believe we're good to go here. So now we're going to just plug in our bounds. So arc sine of 9/4 minus 3/2 over 3/2 minus arc sine 3/2 minus 3/2 over 3/2. Well, that's just 0. Arc sine of 0 is 0. And then, so I just need to clean this up. Arc, this is me arc sine. I can go ahead and just reduce this. This is 9/4 over 3/2 is 3/2 minus 1, because I just divided them both by 3/2. So then this is arc sine of 1/2, which, anyone remember arc sine of 1/2 is? Anyone? Pi over 6. Whew, man, that's kind of a lot. All right, so that's kind of blending in all the things, finding the area using our bounds, and then completing the square to get it into arc sine, and then taking the derivative from there. I do have one more example. I'm actually just going to post that on Canvas because this video is already getting kind of long. So, and it's an arc secant situation, so you don't really need a whole lot of guidance on that one, but because we won't see those very often. So anyway, as always, Prof. Rob Bob, Khan Academy, Calc Chat, Calc View, those are your resources.